In this video, we want to cover some explicit examples using Snell's law to calculate angles of incidence and refraction in different materials. And so once again, Snell's law states that N1 sine theta 1, let me see if I can write that a little bit better. And maybe let's keep that ribbon pinned because I may be erasing a lot here. So N1 sine theta 1 is equal to N2 times sine theta 2. And you can think of the one subscripts as your incident medium and your two subscripts as your refracted medium. So as a quick example, suppose we have air and it has a boundary with water, and we will let N1 be in the air and N2 be the water. And we will also say that N1 is approximately equal to 1, and that N2 is about 1.3. Okay, so in this example, our water is going to have 1.3 index of refraction, and a normal. I need to draw a normal to the best of my artistic abilities. And let's say we have a beam of red laser light come in. And this beam of red laser light has an angle theta 1. And I'm going to let theta 1 equal 45 degrees. Okay. What is theta 2? At what angle is the light going to be refracted inside the water? So if we apply Snell's law, we have N1 sine theta 1 is equal to N2 sine theta 2. And it's this theta 2 I'm solving for, so I divide both sides by N2. Let's do this. And then I'm going to take the inverse sine of this. And I would encourage you to get in the habit of writing things down in this fashion because even though our N1 is going to drop out, right? It's just 1, so it just fades away. But not every time will that happen. And so as a result, this is the general formula, and it's good to derive the general formula and then understand what factors you can ignore or what factors go to 1, etc., etc., etc. So in this case, since N1 is 1, theta 2 is going to equal sine theta 1 divided by N2. And recall that if theta is 45 degrees, the sine of 45 is the same thing as the square root of 2 over 2. So this is the same thing. Whoops. This is the sine inverse of all that. So I have the sine inverse of root 2 over 2 times 1.3. Okay. So this 2 comes from the 1/2. The 1.3 comes from N2. And plugging this into a calculator. Now this should be smaller than 45 degrees. right? That is the expectation. And so if I do this and take the inverse sine, I get 32.95 or approximately 33 degrees. Okay, so my refracted beam is going to do, maybe not quite that sharp. My refracted beam might do something like this. Okay, and this is now theta 2 at 33 degrees. Okay, now my artwork is not that on point, but you can see what's happening here, right? You can see what's happening here. But this is not always going to be the case, right? So for example, what's going to happen if I have a situation where I'm in water and I go into glass? Actually, let's go from glass into water. Let's do that. So let's say I have a boundary here, and down here is water. And again, we'll let N2 be 1.3, and we'll let N1 here equal 1.5. So there's some sort of glass here, and I have my normal, and my incoming ray, and we'll keep things at 45 degrees. That's not 45 degrees. That's closer to it. And so, whoops. That arrow is pointing the wrong way. There we go. And the angle is going to be 45 degrees. And once again, we're solving for N2. I want to know what the refracted angle is. And because we're going from a more dense medium to a less dense medium, this now should be bigger than 45 degrees. Okay. And so if I plug into the same formula, N2 is going to be the sine inverse of N1 sine theta 1 divided by N2. Well, now the ratio of N1 over N2 is going to be less than 1. And that's when you take the sine inverse. That's what drives N2 into a larger value. Okay. So this is going to be the sine inverse of 1.5 times square root of 2 over 2. So this is again going to be root 2 over 2 times 1.3. But we have the extra 1.5 in there now. And when I do this in my calculator, I'm going to get, so I'm going to take 1.5 times the square root of 2 and divide that by 2, divide that by 1.3, take the inverse sine, and 54.675. So we can say that that's approximately, if we want, 54.7 degrees. Okay. And so now this is going to bend outward. Okay. So the moral of the story here is that when you go from a more dense medium to a less dense medium, you're going to bend away from the normal. When you go from a less dense medium to a more dense medium, you're going to bend toward the normal. Okay. So there's an interesting consequence here. If you think about a person standing on a deck of some kind and there's a fish in the water, okay? Um, if the light from the fish is going to do this, it's going to come up this way, hit the surface here, and draw a normal, and then it's going to bend away from the normal toward the observer's eyes. So the observer actually thinks, if I extend that line, I kind of curved it around the fish, but if I extend this line, the observer's line of sight down, they actually think the fish is right here. So when you're looking at fish from above, the fish is actually going to be in front of where you think it is, right? And this is purely a consequence of the way that refraction works. Um, and we also have the issue of total internal refraction. So let's explore that for a moment. And so let's, in this case, let N2 be air, and let's let the incident be glass, and we'll let this have an index of refraction of, again, 1.5. So I'm going to put a normal here. And so the question is, right, as we saw, if I have a slight angle here, then this is going to get bent away. But if I increase this angle, this is going to keep getting bent until the sine of this angle is 90 degrees, or the angle is 90 degrees and the sine is 1. Okay, so the question is, when does that occur? Right? When does that occur? Total internal reflection occurs when theta 2 is equal to 90 degrees. Okay, so total internal reflection occurs at the condition of this, right? And so what that means is you can solve, if you know your two indices of refraction, you can solve this equation for theta 1, and you will always be able to predict at what angle light will then move across the boundary between the two media, and you'll get this. So in our case, what is this critical angle? Okay, what is this critical angle? Well, in our case, theta 1 is going to be the sine inverse of 1 divided by 1.5, which is the same thing as taking the sine inverse of 2/3. So if I take the sine inverse of 2/3, I'm going to get 41.8 degrees. So what that means is, if I have an angle of 41.8 degrees, that means that the refracted light beam will simply move across. And if I have a light beam at a more extreme angle than that, then it will simply get reflected. And angle of reflection will need to match the angle of incidence. It's you might have to forgive my artwork. That's probably a little bit better. So once you increase past this critical angle, okay, then you get total internal reflection. And this angle and this angle are the same, right? And that incident angle for the blue light is going to be larger than the critical angle between the two media. So that is the issue of total internal reflection. So that is some examples of Snell's law and the issue of total internal reflection. Um, so if you have any questions, drop them in the comments, and we will see you in the next video.